the to the optimal control problem, and probably state on the maximum principle. What is this about it? What is the thing correspond exactly like Lagrange integral? How it goes? Difficult. As I said, optimal control is too vast an area. With so many diversities and so many applications. So even to give a quick review in these 2 lectures is not possible. So we are not even going to make an attempt to tell you everything and various types of things. So probably you have to spend quite a bit of time to get some idea, at least 1 year of a good coursework, starting with the Sobolev spaces and PDE and then come to things. So what you are seeing is some glimpses of here and there. So if you are interested, some of you want to do research eventually, that's welcome. That's the purpose of whole of this workshop. Yeah. So what how does it a control system? So we'll go to just optimal control. Now I don't think you need more motivation. You have plenty of problems from engineering sciences if you want to motivate yourself. Practical things. If you don't do it here, you can read books like Sontag and many things if you want to get it. So basically you have a, so as I told you, I want to have the dynamic view. So you use the variable chi now, independent variable instead of x. And your trajectory is x. So your trajectory is evolving. So yesterday you were telling that in the calculus of variation, you have a family of trajectories, and for that you are trying to minimize it, J1. So the y of x is x of t today. Okay. So x is the trajectory. So trajectory evolves from some point according to a dynamical system. So a control system, any control system which you will see, you will have a dynamics. What are you going to see next week also? There the your dynamical system will be an Navier-Stokes equations or Stokes equation, Navier-Stokes or stochastic Navier-Stokes equation. We don't get into that right now. So you will have an equation of this form described by a dynamics fg and then there will be a parameter which we call it control. So this is the dynamics control system describing the trajectory, and this is the control variable. That is how you get, and you have seen that applying control, and you will have an definitely control is started. So your trajectory is starting at the initial time from the initial point x naught in Rn. You can think that. So the trajectory evolves according to that one. So if you changes, you will have different trajectories, and corresponding to that, so the better way, u is the first one. Given u, there is an x. So you can write here ju. That's nothing but, of course, j depends on y, u. It also depends on your x. And you can have a function. So that is where we will have. So basically there are different types of functionals. So let me write down one form typically. I will make some comments here. So I want to use that. So you will have L of t, x of t, u of t, plus you will have another term if you want it, what is called k of t1 x1. Okay. So what is this? What the control is written? This is one form is called the Bolsa form of the cost functional. This is the cost functional. And this L is called the running cost because you are having the cost involved. If you apply this is called the running cost. This is the terminology from the application. When you are doing that, when you are doing something each time, and one finishes, and this K is called the terminal cost. Because as the speakers just start using these terminologies, so it's better that you get to know what are the words they will be using. So you are interested in minimizing u over some class of functions. Okay, so we want to just describe that. You want to make remark. something. So the xt trajectory will be in R. And you may not have the control variable if you want, if you may have many directions. But if you want to control in many directions, it's not necessary that you need that many controls. So ut need not be in Rn. Ut will be in Rm. And you always prefer to have some control or controllability with as less controls as possible, right? You want to achieve that. You don't want too many controls. So it will be belongs to certain set U, and that will be normally M is less than N, but in general M is less than N. So that's a kind of system moving. And X naught is in Rn or some set. There are too many variations, I'm telling you. It's not that X naught is arbitrary. You can take a set, the initial conditions may be in some set, maybe closed, convex, all that, and the final thing will be in thing. Similarly, T1, so where is T1? So T1 is the final time. You do not know whether final time is fixed, and there will be a final state. All that are all different. It poses different types of control problems. So, for example, if T1, if you don't fix it, it will be a free time problem. If X1 you don't fix it, it will be a free state. So, you are not demanding. Okay. If you fix it, it's a free time and free endpoint and free end time problems. All that will happen to you. I will come little more remark on that. I can consolidate that everything by introducing the concept called target set. We'll do that. Before that, I want to tell. If k is equal to identically 0, that means there is no bonus for you when you win the match. You win it, as soon when you go, you get the, your thing. Okay. Then the form is called the Lagrangian cost functional. Lagrangian cost functional. And if L is 0, there is no running cost, only you will get the final bonus. That means your thing, you see, you can have even this one. All this depends on you. You have to think that. Because x1 is nothing but x of g1 basically. x1 is eventually x of g1. And x evolves according to u. So these are all depends on, the u is there implicitly. You don't see that one. So then it is called the Mayer form. And if I remember correctly, this is the first form Pontryagin derived his Pontryagin maximum principle. We are going to, that's okay, it's only a little bit of changes here and there. We will do it something like a Lagrangian cost function. But Pontryagin derived it for the Mayer form. That means that your Ju is just k of T1 x1. But the interesting thing is that you can come from like one cost functional to another one very quickly. It doesn't matter by introducing. Suppose for example, like if it is a Lagrangian cost functional problem, you can convert that into a Mayer form type. And if it is a Mayer form, you can also go back to the Lagrangian. Okay. Suppose it's a Mayer form, for example. Mayer form means L is 0 and you have a k of T1 x1. Your J of u is equal to k of T1 x1. But k of T1 x1 you can quickly write down k of T0 x0 plus integral of T0 to T1 kt, right? Yeah, k differential with, of course, this also depends on t, so you have an implicit t. So k, you can have that kt at T1 x1. You can evaluate that. So if you expand it properly, you will get kt plus kx into x dot. You can do that. So this is nothing but you get kt plus kx into x dot. X dot is nothing but f. So this is your cost function. And this is independent of the control. So minimizing this one or minimizing this one is the same. As soon as you want to minimize the cost function, if you add any constant, it doesn't affect the minimization problem. Okay. So it's a Mayer type. So instead of this one, you can replace with this one. So you have a Mayer Lagrangian type cost function. You get that point? No. Suppose you have a Mayer cost functional. What is the Mayer cost functional? Did you understood Lagrangian and Mayer? Lagrangian means if the cost functional only has this term, not this term. Okay. So and Mayer means you don't have L, only K is there. So assume your cost functional is of Mayer form. That means L is 0. So you are trying to minimize this. Now I am writing this in this form. This is your fundamental theorem of thing, right? Calculus. You write it and expand. And this is a constant. What I am saying that any minimization problem, minimizing Ju, or if you minimize Ju, applications to control problem. Exactly control problems you want to have controls, if possible discontinuous controls, right? Because that's a very natural thing, the famous bang control. So if you want to, even it restricts functions of this form. You see, even if you want the differentiability of your calculus of variation, even such simple functions like LU equal to mod U are not allowed because you don't have the differentiability. So one of the major issue is that regularity thing. The bang control is a. This again, it's very quite intuitive. Suppose you are designing a trajectory and the trajectory is going. The best way to understand that if your student or children is doing very well, you don't have to go and disturb him all the time, right? That means you don't apply any control. The moment he looks that your trajectory is deviating, if they don't do it, you just give a thing. And then it will go correctly. So that means you don't apply anything and then suddenly you apply. Something like that. On weekends we give assignments for the students. So by the Monday it will be fine, they will deviate and then they don't start doing by weekend, you do it. So it's quite good thing. So that's what you do it, bang control. So the engineers prefers that, a discontinuous control basically. So they want that always to apply +1, -1, +1. That's the best way to do it, right? You do that one. Solve that. That's a one serious issue if you want to perform your calculus of variations. The second one is another issue. If you follow the calculus of variation, even the finite dimensional optimization, how do you do it? You start with an optimal control and then you look for perturbations, right? This is the whole idea of calculus of variation. You look for perturbations in some directions. So if you want to hear the trajectories are, if you want to have, suppose you have an optimal trajectory, and then you want to look for the perturbations of this trajectory. So if you want to really work the calculus of variations, the Taylor series expansion, these things, even if you assume smoothness, you have to, and if you expand this in the Taylor form, you will be getting both x and u. So you need smallness with respect to both x and u. So the perturbations allowed are small perturbations not only in the trajectories, you also need perturbations with respect to the control. But then the interesting point is that you may have the smallness of the trajectory even for large perturbations of control. That's possible. The existence and other things are things. So you may be able to produce small trajectories, the approximation trajectory is small from the optimal trajectory even for the larger perturbations of this control. So you want to somehow incorporate larger perturbations to obtain that one. But then how, so that changes, how do you measure the smallness of the control? Measure of smallness of the control. And measuring this smallness in the continuous or a smooth norm is not the acceptable one, because you can have even the normal C2 or L infinity norm or continuous norm, you don't need it actually. That's what I'm trying to say. You can have, in other words, one of the things, for example, is the looking for the, now you are so familiar with the, so, because these days students are more familiar with abstract things, right? Then these actual things, you start with your abstract space and then, if possible, you study one or two examples, not the way. So you can have the norms, other spaces like L1 or other, where you can measure your thing. So you have measurement of smallness of the control is different. And that's possible. You can have the smallness in the, for one example I am saying, of the control in the L1 norm and other things. But you can still get your smallness of the trajectory in the L infinity norm. It's possible. And that again makes difficulty to apply the calculus of variation problem. And here is that the Pontryagin's contribution is significant. How he manages. So that's why the calculus of variation was immediately was not able to apply it to your optimal control problems. You have to have the more not smooth analysis, which was at the right time in the 1950s. Okay. What else I want to tell you? Yeah. So that may allows me to write my, with this kind of remark, you have to see these kind of points. Probably you may not easily get it, but it's nice to see the significant contribution of Pontryagin. Why it was much more harder. There may be many other points, but these are the few points which I believe is more important. Okay. So I'm starting with, let me rewrite once more. So I have a problem, x dot t is equal to f of t x t u t, and x at t naught is equal to x naught. I'm fixing this also for the time being. So let me write down Pontryagin in that one. And you have the ju is equal to integral t naught to t L of t x t u t dt. Okay. So let me at least write my Pontryagin principle correctly. Okay. So this is Pontryagin maximum principle. So again, it's a necessary condition. Okay, you have to see that it's a necessary optimality condition. So what do you do that? You want to say that assume x star, assume u star from t naught to t1 to Rn, right, to u, which is a subset of Rn, be an optimal control and x star the optimal trajectory. What is the meaning of optimal trajectory? Means you are minimizing this function and u star minimizes this. U star solves the minimum problem. Corresponding to that u star, of course this is implicit. That's a whole difficulty, right? You can't just minimize this because it's implicitly the dynamic. And u x star is a corresponding solution to this one equation. Yeah, here is also stated it's a more of controllability problem. Does there is a u satisfying these two? That's a big question. Okay, that's a controllability question. Then there exists P star, what is called the co-state from T0 to T1 to Rn, and lambda star satisfying the Hamilton canonical equations. Basically, what is that? One, let me write x dot star is equal to hp of x star u star p star lambda star, and p dot star is equal to h minus hx of same thing, with the conditions x star at t naught is equal to x naught and x star at t1 is equal to x1. That's the first thing. And what is your h? And your h is h of x u p lambda is equal to, it's a very nice, it's a natural, you can expect what it is. It is the inner product or the dot product with P will act on the dynamics, maybe T also here, and lambda is corresponding to the cost. L. All right. Probably I would have considered these are independent of T, but not a serious thing, the way I have written. There is a second part to it. That's what the name gives, it's a maximum principle. 2, continuing. That's the first thing. So you have a solution. So the optimal solution is existence of a P star. Okay? And lambda star. The second thing, for each T, you fix T and then maximize the Hamiltonian. View this one. Now this is a mapping I am considering H to X star of T, U, P star of T, lambda. Okay? So fix a T, control is given, this is given. Look at this a function of U. So only thing one. What do you mean that for each T, the maximization with this function with respect to U gives back your control at that time. That's a thing. That's what the whole part. Then U equal to U star T, because the maximum will depend on T. For each T, I fixed everything. This is fixed, this is fixed, this is fixed. And U is, this is now maximization in the RM. Nothing you are doing. There is no dynamic maximization right now. For each T, you are doing a maximization. Okay? And H of X star of T, U star of T, P star of T, lambda star is equal to maximum over U of that. You see? That's what the maximization. This is the kind of optimality constitution. But then the impact was the thing. First of all, proving that it was difficult. And second thing, the engineers were the happy thing. You have a necessary condition. You do try to maximize. The moment you maximize, there is a hope to get something. It doesn't give you the control. But then, depending on the problem you study, you may be able to construct the control successfully to many applications. I'll just present one example little later. Before that, let me give you two more remarks. One more. That's more crucial. Proof you can read and work it out. If I start giving the proof, probably you need I'm sure you may need more than an hour. You want to give a complete proof. They don't give that much time to me to do it, right? Want to prove it next class? Can prove it. All right. So one thing one or two remarks which you have to be to understand. Why this is P star is called the costate vector. P star is called costate. I'm using again, you are sure to hear these terminologies. Costate, it's also called the adjoint. It's an adjoint equation. And when you go to PD, you can see that it actually solves an adjoint equation. Maybe tomorrow we'll see the controllability. Okay, but when you go to especially heat equation and other things, because you have to be careful with your initial or endpoint condition. It's called the costate. One thing yesterday I remarked, but again once more I want to remark that point. So I deleted. So what is the constraint here? The constraint is this one. This is the main constraint, right? F of T x T ut. So if you recall the concept of calculus, so you have to adopt that technique. If you recall the concept of Lagrange multiplier. What is Lagrange multiplier done? For each constraint, you add a lambda and sum it overall. That's what you got it. You have added sigma lambda I, the gi of x. But here for each t you have a thing. So for each t you need to have a Lagrange multiplier, and then you have to sum it in a continuum fashion, naturally an integration, and that's what it is used. So the one of the things is used first to add this constraint and make it a basically an unconstrained problem. So with the cost functional, you add a basically a term of this form. This is what you expect. Pt into x dot t. So these are all part in the proof you will see. You have to add a term. That's a natural thing. So exactly you are adding a term of that one and proving this existence for the unconstrained problem, and then the variations properly. And that leads to this state existence of P star. So P star has to be there. So it's quite natural extensions coming from the fundamental calculus of variation problems. The expected one. Okay. That's the first point I want to tell you. Second point, that's also very crucial. Why this? What is the kind of the Pontryagin maximal principle is so important compared to the calculus of variation? There is one kind of fundamental difference probably you can observe. If you look at the yesterday's calculus of variations, let me write down the Hamiltonian. That's why I used a different H here. If you recall, essentially the Hamiltonian define is a maximization. Do you recall the thing? P dot of psi minus L of P dot of psi minus L of psi. We recall the Legendre transformation. Okay. Before that, I introduced in terms of Ly prime, but fundamentally this one actually. So you are maximizing a Hamiltonian with respect to your Lagrangian, and then writing down the Hamiltonian canonical equations for this Hamiltonian function. And so a maximization procedure is done in the beginning, and then you write down the Hamilton's equation. But when you come back to your Pontryagin maximum principle, you have introduced your Hamiltonian without any maximization, and then you write down the Hamilton canonical equation, and the maximization is a consequence, you see. And this has an effect because of the regularity, because when you try to maximize something, even if a smooth quantity, the maximum thing will lose its smoothness. So there is a possibility quite often that this set you get it even if it's a smooth thing, you may not have. That's also you observe the way you write it, right? In the beginning it is written as Ly prime. So L has smoothness, Ly prime will not have smoothness. So the Hamiltonian which introduced in the previous case, there is a chance for losing its smoothness. But here, the moment you have F and L are smooth, you will be able to get its smoothness for the Hamiltonian. So that's another advantage it might have it. And one more point. One more point regarding this initial condition. This is a 2n system, right? Star is a 2n system of ODEs, right? 2n system is a system of 2n ODEs, right? Is a system of 2n ODEs. So naturally you need 2n conditions, right, for unit, and that's provided here. You see, so you have these are n conditions. It's also provided n condition. That's why you don't see any conditions for P. It's implicitly given through X. But that's not the case all the time. I want this maximum principle. How do I delete? Alright. There's a board here, right? All right. So, but suppose it's not the case. You have, I want to give you a particular situation. Suppose your target set is not that one. Suppose you are taking a target set, S is equal to T0 to T1, T0 to T1 cross some M, where M is k dimensional. You see, you are taking that one. Then you don't get this condition, because that's part of the analysis. You can write down, that may not be difficult. So what you can do is that you study this proof of this maximum principle, and that may be easier to write down that condition. What you will get is something this way. What you can prove here, x star of T1 will be in Sm. You can prove only that. You will not be able to prove x star of T1 is equal to x1. That's a target set, right? So you want x star of T1 is in M. That will. But M is k dimensional, so this is only k informations. It gives you only k conditions, not more than that. So you have to look for, this gives you k conditions. So you need to have another n minus k conditions. Right? And this is come by what are called the transversality condition. You have to derive these extra conditions, transversality conditions. And that is given in terms of your costate. So you get some costate conditions. This is nothing but you get P star of T1 D will be 0. This for all vectors D in the tangent space now, x star of T1 to M. So you get conditions, transversality. This is the condition you should derive from I'm writing a second Pontryagin maximum principle basically. Okay, this is the one Pontryagin maximum principle. In that case, when you have your target set as this, this just to show that even a small changes in that one, your things will get changed. Okay, so you have your conditions here for all D. How many conditions are there? Because M is k dimensional, this is k dimensional, so it's orthogonal to k dimensional space, so it has to be n minus k dimensional. So this gives you n minus k conditions. Say for example, suppose I take S1 is equal, M is equal to Rn. When M is equal to Rn, your tangent space is the same space. So you have your P star of T1 D is equal to 0 for all D in Rn. So that will imply P star of T1 is equal to 0. In that case, you don't have any condition like that. So naturally, right, x star of T1 is given to be in Rn. That means that there is no information. That's the meaning, right? When you say that, do you understand when I say these conditions? When I say that x star of T1 is equal to M, it is actually an information. It is k informations. But when I say that x star of T1 is in Rn, it has no information. Is there that something like that you are in this campus? Doesn't give that you are here, right? Doesn't give, you are in the universe, that's it. But the moment you say that it is here, you are here. Okay, so that's what it says. So there is no condition here, and the condition can replace here. Okay. On the other hand, if you take M equal to x1, what does that mean? This is a singleton, so that this has no information basically. That means all informations are here, and this is the condition which you have derived already. Okay, so you have even for this set, you can immediately write down these things, except that one has to derive these additional transversality conditions are part of the proof. You have to do that. I want to give you one more example. No, one example to before I go to, and that's what I will be talking about, the Pontryagin maximum principle. Because in another talk I have to give you something about the DPP. So you want to just read the notes. I will send some more corrected notes. The notes you already posted is maybe a wrong picture in the second time. The second picture is may not be the correct one. I didn't see the posted one. Twice I sent them. But I made some more corrections, so they will be updating the notes. Okay. Here is a nice example. How the Pontryagin maximum principle can be used to solve the problem completely. Very easy example. Dx by dt is equal to xt ut. X at t naught is equal to x naught. With your ju is equal to integral t naught to t1 1 minus ut into xt. Okay. So this also has some physical applications. You can see that xt is your output grains or whatever it is, which you can consume, eat. Okay. But when you have a factory, you don't want to eat everything, right? You want to reinvest a fraction of it. How do you reinvest so that we should maximize your consumption as much as possible? So ut is basically the fraction you reinvest. Okay. So when you reinvest, this is what you remain. So you want to maximize it. So you have additional condition. You put it. Problem is simple. If you didn't understand, fine. It's a nice thing for you to go and write down everything. But it's a very easy problem to tackle this one. So just try to do that one. So let me write down what is your f of xu. This one, right? Just xu. And what is your L of xu? This one, right? 1 minus u into. So can you write down the equations? My Hamilton equations? Assuming that xu is a maximum. I am not putting star. Now assume that it has a solved x star u star replaced by x. So can you write down? What is x star? X dot of t? HP, right? This is the equation, right? What is HP? I didn't write your HP. So that also let me give you. H of x pu is equal to p dot, right? F of xu p plus L of xu. You see, that's very easy to write. H of x pu. So what is your H? HP? HB is nothing but F itself, right? So this is xu. And what is your y? P dot? P dot of t is equal to minus hx. What is minus hx? Minus 1 minus ut into pt minus, let me just copy. Am I right? Hx you have to write, right? So you have to write hx is nothing but fxp, that is u, and you can combine. I think I have combined here. You can write down that. That's not difficult. And what are the conditions you have? X at 0, you put t naught is equal to 0 is x naught, and this is the one which I have, it is in this situation because I have not put any conditions. So it's a free time. Yeah, free endpoint problem, not free time, free endpoint problem. So T1 is fixed. So you get this condition. So it's this one because I have not put any target x1. Okay, so you get that. And what is the maximum principle? That's all. We will write the equations, and these are the two things given to us by the PMP. Okay, so you have the problem h of xt pt ut is equal to maximum of u and you have a condition, u should be between 0 and 1. So now there is no t variable. I told you, if you look at the maximization, you maximize it with respect to only that where it belongs to. Okay, that's it. So it's a 0 less, so it's not ut. That's the whole thing it is given. H of xt pt u. But what is that? Maximum of 0 less than or equal to u less than or equal to 1 of xt, h is xt, we are already written here. I have written plus u, maybe some small computation is done here. Let's not do that one. So you can see that this will be that. H of xt pt u will be this one. You just do the computation, just go and do that one. That's it. What BMB is done is that one. Now can we do it little more? That's the question, but that's how the engineers will do. Then you have to use the easy nature of the problem. If I get time, maybe in the second hour after DPP, if LQR, if I can go, I will do you something. One more example in the LQR, linear quadratic regulator problem. But at that I am sure I can reach there. Okay. But here you have to prove, so as far as the maximum principle is concerned, this is what it will write. This you can write the moment you have a Pontryagin maximum principle. If x and pt is the optimal, you are the optimal control, and such a system will satisfy this one. Now we have to, if you want to do a further analysis, you have to do cleverly looking at the informations available. Looking at the whether our, because our system is very easy, it's not very complicated, and you also have the Hamiltonian in a very easy form. This is what we are going to explain. And also the equation, we will soon see that the P dot T getting is in a very nice form. So you have to understand very cleverly the nice forms available there, and then you are trying to solve it. So what does this immediately tell you? You are trying to maximize this one. So the moment is a very interesting thing. This also gives you an example how the control irregular can be. Okay, how the classical things can be. So that's why this example is taken. This can be maximum when this is positive. The best maximum thing is u equal to 0, right? Okay. So this whenever this is positive, the choice or the best choice of u is equal to 0. Whenever this is negative, the best choice is 1, because it gives you the maximum. So if you want to maximize this, you have ut equal to 0 if pt is positive. Pt is greater than or equal to 1. Pt minus 1 is positive. And c equal to 1, you see it's exactly like a Big Bang control. Unless it is entire place, it is 0. Or unless ut is 0.
1, right?
Yeah, it's 1.
The previous one.
Okay, fine. Fine. If, yeah, pt is less than or equal to 1. You see? Of course, still we are in trouble because you don't know what pt is. Everything is implicit, right? pt, xt, ut are coupled. It's nothing is decoupled so far. But we have first information about the control. And it looks like that it has a Big Bang type control unless pt remains greater than or equal to 1 or pt remains less than or equal to 1. Okay. Now we have to use the second step in that. That's one thing, information. Second step, you use this condition now. Your pt1 is 0 at t1. So you are doing a reverse thing. pt1, so you are solving from t0 to t1. At pt1 is 0 and p is continuous, p will remain to be 0 at least some point, right? So you have some t close to t1, pt will be 0. So that allows you at the end point, your ut will be 0. We don't know how far you can come, but you can come to some stage. At least there is an interval in which it is ut is 0. In other words, at this interval, pt is less than 1. Not trouble. Okay? So the moment now you are, so that's the first second information used.
You're saying that close to small t1
Will be less than 1.
less than 1, right?
Oh, I didn't write. Yeah, that's I wrote it correctly there. Here. Okay. Yeah, it's this one. This is the correct one. Since PT1 is 0, PT will be less than 1, close to that one. So in that interval, your UT is 0. The moment UT is 0, this vanished. The entire control disappeared, your PT equation. That won't happen in general. Okay. For this case, so at that interval, your P dot of T will be minus 1, which can be solved, you see. So you can actually solve your PT in a small interval, which will give you nothing but T1 minus T or whatever it is, right? PT may be T1 minus T. And then this will remain to be less than 1, 0, in some up to T1 minus 1. So you will, this you can do, it's a small work. The main ideas are given. From here, you can come up to T1 minus 1. You can exactly recover that. And at that point, your PT1 will be 0. And then you can proceed further and you will get, after that, you can choose your UT to be 1. So you have initially, you can exactly calculate, that's what I'm saying. So I'm leaving a small part of that. The second part as an exercise. From T1 minus 1 to come, and then you can solve this equation again. And because that point, UT will be 0, right? UT will be 1. Okay. So you will have exactly, you can solve your UT1 and you can solve this equation. Because UT is, you know this is 1, you can solve this equation in terms of the exponentials. And you can get your thing and you have the control. So you have a completely band computing. This type of control. You see, band type control. And that's reasonable as far as this industrial production is concerned, right? So what are you doing initially? So when you start a factory, the message is that don't buy your home product from the factory investment. Whatever you get it, you reinvest there. Okay, when your thing is fine, you don't invest anything, you take back. It may not work in very thing because it's a very simplified model, right? You may have to keep on. In the simplified model, you have the, so this is what most of the time you have to do it. You have to do the simple nature of the, or the nature of the problem, get the information from there and try to solve the problem. So the maximum principle helps you eventually to reconstruct your control, cost state, everything. But it's no longer easy.
So what about the lambda range?
Which one? Lambda, there are some remarks which I have not mentioned here. I think in quite often you will be able to choose your lambda star maybe minus 1 or something. And you should be, there are some more conditions which I write. The lambda star P star should not be 0, 0. And using that you can actually, lambda star can be taken away. Putting some constant minus 1 or something. So these, most of the problems it doesn't appear. But it's not a complete theorem. So the correct theorem is stated in that one. But in many cases you can incorporate lambda star with somewhere else. You don't need it. But then there are problems with your P star, you may need a lambda star. Okay, so that's why in the general setup, you need that to write the general theorem. P star can vanish, which doesn't tell anything. So you can do that. So maybe I will start after that, if you want to have tea, or I can go to DPP, introduction to DPP. It's time or not? Okay. Then after tea? Okay. Yeah, I start so it's better 1 hour.